Hello, and welcome to the Sleepy Astronomer. I'm so glad you found your way here. Tonight, we aren't simply stargazing. We're exploring something stranger, something invisible, something that makes up most of the universe and is tearing it apart. Tonight, we're drifting through 100 gentle facts about dark energy, the mysterious force that fills space, accelerates galaxies, and determines the fate of everything. It doesn't pull things together, it pushes them apart. And the universe is speeding up because of it. 100 facts that build toward understanding, each one a piece of the puzzle, revealing how we discovered the invisible force tearing the universe apart, why it challenges everything we thought we knew, and what it means for the ultimate fate of all existence. If this is your first journey with me, welcome aboard. And if you've travelled with me before through the quiet wonders of space, it's wonderful to have you back among the stars. If this exploration helps you unwind or fills you with quiet wonder as you drift towards sleep, feel free to give the video a like. And if you'd like to help others discover these peaceful cosmic journeys, a subscription truly helps this little corner of the universe grow. So, settle in, find your most comfortable position and let your thoughts drift as we begin our gentle journey through 100 facts that reveal quiet mysteries of dark energy, the force that shapes everything while touching nothing, the energy of emptiness that determines the destiny of the stars. The universe isn't still. It never has been. Right now, as you listen to this, space itself is stretching. Galaxies drift farther apart with each passing moment, not because they're moving through space, but because the space between them is growing. It's happening everywhere, all at once, in every direction you could possibly look. This expansion isn't new. It's been happening for nearly 14 billion years, since the moment of the Big Bang. But here's what makes it strange. The galaxies themselves aren't moving. They're standing still in their local patch of space. It's the fabric of reality itself that's stretching, carrying them along like boats on a rising tide. Space expands, and everything embedded in it drifts apart. For most of the 20th century, astronomers thought they understood what was happening. The universe was expanding, yes, but it had to be slowing down. That's just physics. Gravity pulls everything together. Every galaxy tugs on every other galaxy, and that collective pull should act like a brake on cosmic expansion. Like throwing a ball into the air, it goes up, but gravity slows it down, eventually stopping it and pulling it back. The universe should work the same way, expanding outward from the Big Bang, certainly, but decelerating under the weight of all that matter pulling back. Every astronomer expected this. Every cosmology textbook taught it. The expansion was real, but it was winding down. The only real question was, how much? Would the universe slow enough to eventually stop and collapse back on itself in a big crunch? Or would it coast forever, expansion gradually approaching zero but never quite stopping? Those were the only two options anyone seriously considered. Nobody, absolutely nobody, expected what they actually found. In the 1990s, astronomers developed a way to measure cosmic expansion with extraordinary precision. They used type E or supernovae, exploding stars that shine with predictable brightness. These stellar explosions happen when a white dwarf star pulls too much matter from a companion and crosses a critical mass threshold. When that happens, the star detonates in a thermonuclear explosion so consistent that every type Ia supernova reaches nearly the same peak brightness. They're cosmic lighthouses, standard candles burning with known luminosity across billions of light years. Think about what that means. A star explodes in a galaxy so distant its light has been travelling toward us for billions of years. That explosion briefly outshines the entire galaxy it inhabits. For a few weeks, a single dying star becomes visible across cosmic distances that would render whole galaxies invisible. And because we understand the physics of how these stars explode, we know exactly how bright that explosion should be, not approximately, precisely. Here's why that matters. If you know how bright something actually is and you measure how bright it appears from Earth, you can calculate its distance. It's the same principle as seeing a distant street light and knowing how far away it must be based on how dim it looks. These supernovae became perfect cosmic rulers, allowing astronomers to measure distances across the observable universe with unprecedented accuracy. By comparing the apparent brightness of these exploding stars to their distance, measured independently through redshift, astronomers could trace the expansion history of the universe. They could see how fast space was stretching at different points in cosmic time. It was elegant, it was precise, and it was about to overturn everything. In 1998, 2 independent teams announced their results. They'd been studying distant supernovae, measuring their brightness, calculating their distances, mapping the expansion rate across billions of years of cosmic history. Both teams found the same shocking result. The supernova appeared dimmer than expected, not by much, but by enough that the discrepancy was undeniable. Dimmer meant farther away than the models predicted, and farther away meant the universe had expanded more than it should have. The expansion wasn't slowing down, it was speeding up, accelerating. The universe was moving faster now than it had been billions of years ago, and that made no sense at all. There was no theoretical framework for this. No one had predicted it. No one had even suggested it as a possibility worth investigating. The teams had been searching for deceleration, trying to measure how much the expansion was slowing so they could determine the universe's ultimate fate. Instead, they found acceleration. It was like setting out to measure how quickly a car was braking and discovering it was actually pressing the accelerator. Gravity doesn't push. It only pulls. There was nothing in the standard model of cosmology that could explain acceleration. No known force, no physical mechanism. The discovery violated every expectation, contradicted every prediction. It was as if you'd thrown that ball into the air and watched it accelerate upward, faster and faster, defying gravity and common sense. The cause of this acceleration, whatever it was, received a placeholder name: dark energy. Not because it's literally dark, but because we don't know what it is. The dark means unknown, mysterious, invisible to all our instruments except through its gravitational effects. It's out there, filling space, pushing the universe apart, and we have no idea what it actually is. This discovery didn't just surprise astronomers, it stunned them. It won the 2011 Nobel Prize in Physics because it fundamentally rewrote our understanding of the cosmos. We thought we lived in a universe slowly coasting towards stillness, gradually running down like a wound clock. We actually live in a universe accelerating towards something we can't yet comprehend. The cosmic engine isn't winding down, it's speeding up. Everything we thought was wrong. And that wrongness opened the door to the greatest mystery in modern cosmology. The discovery was so unexpected, so paradigm-shattering that it took years for the scientific community to fully accept it. But the evidence kept mounting. Other teams verified the results. More supernovae were observed. Different analysis methods were applied. The data became undeniable. In 2011, 13 years after the initial announcement, the Nobel Prize in Physics was awarded to Saul Perlmutter, Brian Schmidt, and Adam Rees for the discovery of the accelerating expansion of the universe through observations of distant supernovae. That's how significant this was. Nobel Prizes don't come quickly in physics. They wait for confirmation, for certainty, for the dust to settle and the revolutionary to become routine. This discovery did more than add a footnote to cosmology. It rewrote the textbooks. It forced physicists to confront the uncomfortable fact that we don't understand what makes up most of the universe. It revealed that something invisible, something we'd never detected, was dominating cosmic evolution on the largest scales imaginable. The term dark energy emerged as a name for this mysterious force. It's not a particularly helpful name, honestly. Dark just means we can't see it, can't detect it directly, don't know what it is. It tells you more about our ignorance than about the thing itself. But it's stuck. Dark matter was already taken. That's the invisible stuff holding galaxies together through gravity. Dark energy is different. It's the invisible stuff pushing the universe apart. Two dark unknowns, opposite effects. We're really quite good at naming things we don't understand. What could possibly cause this acceleration? In the scramble to explain it, physicists dusted off an old idea from Einstein's original equations. Back in 1917, Einstein was working on applying his new theory of general relativity to the entire universe. This was bold. No one had tried to describe the whole cosmos mathematically before. But Einstein had a problem. His equations predicted that the universe should either be expanding or contracting. It couldn't just sit still. Gravity pulls things together after all. But in 1917, no one knew the universe was expanding. Hubble's observations were still more than a decade away. Everyone assumed the cosmos was static, eternal, unchanging. Philosophers had thought so for millennia. Astronomers saw no evidence to the contrary. The universe just was, permanent and stable. Einstein needed his equations to allow for a static universe, so he added a term, a mathematical fix really, called the cosmological constant. This constant represented a kind of energy built into the fabric of space itself, creating a repulsive force that could perfectly balance gravity's pull and keep the universe frozen in place, push and pull in eternal equilibrium. Nothing moving, nothing changing, just stillness across infinite space. It was an elegant solution, a bit artificial perhaps, but it worked mathematically. Einstein published his static universe model, cosmological constant and all, and moved on to other problems. He didn't particularly like the constant. It felt like a fudge factor, something inserted not because nature demanded it, but because his assumptions did. Still, it did what he needed it to do. Then in 1929, Edwin Hubble made his famous discovery. He'd been observing distant galaxies with the Mount Wilson telescope and noticed something remarkable. They were all moving away from us, not some of them, all of them, and the farther away they were, the faster they appeared to be receding. The universe wasn't static at all. It was expanding, stretching, growing larger with each passing moment. Einstein's static universe collapsed overnight. He no longer needed the cosmological constant to hold things still, because nothing was still. The universe was already doing exactly what his original equations predicted. Expanding, evolving, changing. He removed the constant from his equations and reportedly called it his biggest blunder. For 7 decades, that's how history remembered it. Einstein's one great mistake. The cosmological constant became a footnote, a cautionary tale about letting preconceptions override mathematics. It was dead, forgotten, erased from the story of modern cosmology. And then 1998 arrived and brought it back from the grave. Here's the beautiful irony. Einstein added the cosmological constant for completely the wrong reason. He wanted to stop expansion that was actually happening. But the constant itself, that turned out to be exactly what we needed, just not for the purpose he intended. In 1917, Einstein thought it could freeze the universe. In 1998, we discovered it might explain why the universe is accelerating. Same mathematical term. Completely different physical meaning. Einstein was right about the constant existing, wrong about what it did. How many scientists can claim their biggest mistake turned out to be correct? The cosmological constant stands as physics' greatest resurrection story. What Einstein considered his failure became one of his most profound insights. He invented the right answer to the wrong question, and it took us 80 years to figure out what question it actually answered. The constant now represents dark energy in our modern equations. It's the simplest explanation for cosmic acceleration, a constant energy density that fills all of space. Not matter, not radiation, but energy inherent in the vacuum itself. This energy density remains the same everywhere, unchanging through time. As the universe expands and matter spreads out, becoming more dilute, the dark energy doesn't dilute. It stays constant. Every cubic meter of space contains the same amount of dark energy, whether that space existed 10 billion years ago or will exist 10 billion years from now. That's what makes it so strange. With normal stuff, matter, radiation, even dark matter, expansion dilutes it. Double the volume of space and you halve the density of everything in it. Pour water into a large container and it spreads thinner. But dark energy doesn't work that way. Double the volume, and you've just doubled the total amount of dark energy in the universe. It's created somehow as space itself expands. Or maybe it was always there, woven into the fabric of reality itself, invisible but fundamental. After 1998, teams around the world began confirming the acceleration through different methods. Galaxy surveys mapped the distribution of matter across cosmic time, seeing patterns that only made sense with dark energy. The cosmic microwave background, that ancient light from 380,000 years after the Big Bang, showed temperature patterns consistent with a universe dominated by something we couldn't see. Everywhere astronomers looked using completely different techniques and instruments, the evidence aligned. Something unseen was dominating cosmic behavior on the larger scales, and that something was making space expand faster and faster. Einstein's blunder wasn't a blunder at all, it was prescient. He was right for completely different reasons than he thought, but he was right. The cosmological constant exists. We just didn't know we needed it until 70 years after he invented it. The evidence kept coming from every direction. It wasn't just those two supernova teams. Independent observations using completely different methods kept pointing to the same conclusion. The universe is accelerating. Something invisible is pushing it apart. Galaxy surveys revealed patterns in how matter clumps together across cosmic distances. These patterns only made sense if dark energy was real, dominating the universe's behavior on the largest scales. When astronomers mapped millions of galaxies and measured how they cluster, the distribution matched predictions for a universe with dark energy. Without it, the patterns would look different. The clustering would be tighter, the structures denser. The math only worked one way. The cosmic microwave background added its own confirmation. This ancient light, released when the universe was just 380,000 years old, carries information encoded in tiny temperature variations across the sky. Those variations form patterns, and those patterns reveal the universe's composition and geometry. The data matched a universe that's about 68% dark energy. Not approximately, precisely. Different teams, different telescopes, different analysis methods, all arriving at the same number. Everywhere astronomers looked, using instruments that measured completely different things, they found compatible evidence. It's one thing for a single measurement to suggest something strange. It's another thing entirely when a dozen independent lines of evidence all point to the same invisible force. The convergence was undeniable. Something unseen was dominating cosmic evolution. This wasn't a measurement error or a calibration problem. This was real. Dark energy was shaping the universe on scales that make galaxies look like dust motes floating in an ocean. So the cosmological constant came back. Einstein's abandoned term, his biggest blunder, returned to the equations as the simplest explanation for what we were observing. It represents dark energy in mathematical form, a constant value that describes the energy density of empty space itself. Here's what makes it elegant. The cosmological constant is just a number, one term in Einstein's field equations. It doesn't require new particles or exotic fields or complicated physics. It's just energy uniformly distributed through all of space with a density that never changes. Simple, clean, mathematically straightforward. This energy density remains the same everywhere and at all times. In the early universe, when everything was hot and dense and compressed into a volume smaller than a grapefruit, the cosmological constant had exactly the same value it has today. Billions of years from now, when the universe is cold and nearly empty and galaxies have drifted beyond sight, it will still have that same value. It's truly constant, which is refreshingly honest naming for once. Unlike matter or radiation, dark energy doesn't dilute as space expands. That's the crucial difference. Matter spreads out. Put 100 galaxies in a box, then double the box's size, and now you have half as many galaxies per cubic meter. Expansion dilutes matter. The same goes for radiation. Light gets stretched and redshifted as space expands, losing energy in the process. Everything thins out except dark energy. But dark energy works differently. It's a property of space itself. As the universe expands and creates more space, it creates more dark energy along with it. The energy density per cubic meter stays constant, which means the total amount of dark energy in the universe is increasing. More space equals more dark energy. It's being generated continuously as the universe grows, or perhaps it was always there, woven into the fabric of space-time from the beginning. We're still not entirely sure which. This is why dark energy dominates now, but didn't always. In the early universe, matter and radiation were compressed into a smaller volume. Their densities were enormous. Dark energy was there too, with the same density it has today, but it was completely overwhelmed by everything else. Gravity from all that matter dominated cosmic evolution. The universe was decelerating, just as everyone expected. But as the universe expanded, matter and radiation diluted, while dark energy stayed constant. Eventually, around 5 or 6 billion years ago, dark energy's density overtook matter's density. That's when acceleration began. Before that transition, the universe was decelerating as expected. After it, dark energy took over and acceleration began. We happen to live in the era just after this cosmic transition, when dark energy recently became dominant and the universe shifted from slowing down to speeding up. Einstein's Blunder captured something true about reality. He added the cosmological constant to prevent expansion, but the constant itself was correct. It exists. It's real. He just didn't know what it actually did. He thought it created a static universe. It actually drives acceleration. Wrong application, right mathematics. Wrong reason, right answer. This might be the most interesting kind of mistake in science, being right for the wrong reasons. Einstein invented the cosmological constant because he needed the universe to be static. The universe wasn't static. His assumption was wrong, but the constant he invented to satisfy that wrong assumption turned out to describe something that actually exists. He was looking for a force to stop motion and accidentally discovered the force that accelerates it. The irony is almost poetic. For 80 years, Einstein's cosmological constant was treated as a cautionary tale about the dangers of letting philosophy override observation. Don't assume the universe is static just because ancient Greeks thought it should be. Don't add arbitrary terms to equations just to get the answer you want. Let nature speak for itself. But it turns out Einstein's intuition was better than anyone realized. The universe does contain a constant energy density in empty space. It does have this strange property that doesn't dilute with expansion. Einstein saw something real, even if he misunderstood what he was seeing. His greatest blunder became his most prescient insight. Sometimes being wrong in the right way is more valuable than being conventionally correct. We still call it the cosmological constant in his honor. Lambda, the Greek letter Einstein used to represent it in his equations. It sits there in the field equations of general relativity, describing the energy of the vacuum driving the acceleration of everything. Einstein's ghost must be having the last laugh. He was wrong about keeping the universe static, but right about almost everything else. So we know dark energy exists. We can measure its effects, trace its influence across billions of years, see it in the acceleration of distant galaxies. But here's the uncomfortable question. What is it? One idea stands out as the simplest answer. Dark energy might be vacuum energy, the energy of empty space itself. This sounds strange at first. How can nothing contain energy? But quantum mechanics insists that empty space isn't really empty. The vacuum teems with activity on the smallest scales, a roiling sea of quantum fluctuations invisible to everything except the most delicate experiments. These fluctuations are real. Pairs of particles and antiparticles constantly pop into existence and annihilate each other in tiny fractions of a second. They're called virtual particles, which makes them sound imaginary. But they're not. They have measurable effects. One of the most famous is the Casimir effect, named after Dutch physicist Hendrik Casimir, who predicted it in 1948. The Casimir effect works like this. Take two metal plates and place them very close together in a vacuum. Not touching, just extremely close, a few micrometers apart. Quantum theory predicts that virtual particles constantly appear and disappear everywhere in space. But between those two plates, only certain wavelengths can fit. It's like standing between two mirrors. Only certain patterns of light waves can exist in that confined space. Outside the plates, all wavelengths are possible. Inside, only some. This creates an imbalance. There's slightly more quantum pressure pushing from the outside than from the inside, so the plates get pushed together by an incredibly tiny force. And this was actually measured in the laboratory, confirming that vacuum energy is real. Empty space has energy. The quantum vacuum is not nothing. It pushes. So maybe dark energy is just vacuum energy on cosmic scales. The energy of quantum fluctuations fill in all of space, creating a kind of pressure that pushes the universe apart. It's elegant. It connects cosmology to quantum mechanics. It would mean dark energy isn't some exotic new substance. It's just a property of space itself that we already know exists on small scales. Problem solved, right? Not quite. There's only one problem. When physicists actually calculate how much vacuum energy should exist, they get an answer that's catastrophically, embarrassingly, spectacularly wrong. The calculation uses quantum field theory, one of the most successful frameworks in all of physics. It's been tested to extraordinary precision. It predicts things like the magnetic moment of the electron to 10 decimal places. It describes the behavior of every particle in the Standard Model with stunning accuracy. It's not some speculative theory, it's the foundation of particle physics, confirmed in countless experiments. So when you use it to calculate the energy density of the vacuum, you should get something close to right. Instead, the calculation overshoots reality by 120 orders of magnitude. That's not a typo. 120 orders of magnitude. The predicted value has 120 more zeros than the observed value. Let me put that number in perspective. An order of magnitude means a factor of 10. 2 orders of magnitude means a factor of 100. 10 orders of magnitude is 10 billion. 20 orders of magnitude is 100 billion billion. We're not talking about 20 orders of magnitude, we're talking about 120. If you predicted someone weighed 70 kilograms and they actually weighed 70 followed by 120 zeros kilograms, that would be comparable to this error. The observable universe contains maybe 10 to the power of 80 atoms. Our prediction is wrong by a factor that's 10 to the power of 40 times larger than that. This isn't being a little bit off. This isn't even being very wrong. This is physics failing so completely that the prediction and reality exist in different conceptual universes. Physicists call this the worst theoretical prediction in the history of physics. That's not hyperbole or self-deprecation, it's just accurate. Some call it the vacuum catastrophe. Others call it the cosmological constant problem. Whatever you call it, it's deeply embarrassing. We can predict the behavior of subatomic particles with incredible precision. We can calculate the orbit of Mercury accounting for relativity to the millimeter. But when we try to calculate the energy of empty space, we're wrong by more than a Google. That's 10 to the power of 100, a number so large that there aren't enough particles in the universe to count to it. Here's the thing that makes this even more unsettling. If the calculation were actually correct, we wouldn't be here to notice. The vacuum energy would be so enormous that space itself would expand faster than light from the very first moment after the Big Bang. No atoms could form, no stars could ignite, no galaxies could coalesce, no planets, no life, no confused physicists scratching their heads. The universe would just be a rapidly inflating void where nothing could ever exist. The fact that we're here, that anything is here, tells us the calculation is wrong. We just don't know why. We don't know what we're missing. We don't know what fundamental principle we've failed to understand. There's a piece of physics, probably a big piece, that we simply haven't discovered yet. This is where physics stands today. We observe dark energy. We measure its value. We know it's about 68% of everything in the universe. But when we try to calculate what that value should be, using our best theories, using frameworks that work perfectly for everything else, we get an answer so wrong it's almost funny. Almost. It would be funny if it weren't our entire understanding of reality at stake. The mismatch is so severe that many physicists suspect there's some fundamental cancellation mechanism we don't understand. Maybe quantum field theory contributions are somehow offset by some other effect we haven't discovered, leaving only the tiny observed value. But nobody knows what that mechanism would be. Nobody has a convincing explanation. We're essentially waving our hands and hoping future physicists figure it out. Yet despite this catastrophic failure, despite being wrong by 120 orders of magnitude, vacuum energy remains our simplest explanation for dark energy. It's the best idea we have. The alternatives either require inventing entirely new physics or admitting that gravity works differently than we thought on cosmic scales. So we stick with vacuum energy, acknowledge that our calculations are horrifically wrong, and hope that someday we'll understand why. This is cosmology's greatest humiliation and greatest mystery wrapped together. We can observe the effect. We can measure it precisely. We just can't explain it. And the gulf between observation and theory isn't a small gap we need to bridge. It's a chasm 120 orders of magnitude wide, and we have no idea how to cross it. Given that our calculations are wrong by 120 orders of magnitude, maybe we should consider alternatives. Maybe dark energy isn't vacuum energy at all. Maybe it's something else entirely. The simplest possibility is that dark energy truly is constant, the same everywhere, unchanging forever, the cosmological constant, lambda. It has exactly the same value today as it did 10 billion years ago, and it will have exactly the same value 10 billion years from now. This is what most observational evidence suggests. Dark energy that just sits there, eternally steady, never varying, filling space with the same energy density from the Big Bang to the end of time. But there's another option. What if dark energy changes? Not constant after all, but dynamic. Slowly evolving over billions of years, its strength shifting as the universe ages. Physicists call this idea quintessence, borrowing from ancient philosophy's concept of a fifth element beyond earth, water, air, and fire. In this case, it's a fifth element beyond the four fundamental forces we know. Quintessence would be a field like the electromagnetic field or the Higgs field, but filling all of space, an invisible ocean permeating the universe, with an energy density that can vary with time, not frozen, not static, but slowly changing. Maybe it's stronger now than it was in the past. Maybe it's weaker. The key difference from a cosmological constant is that quintessence can evolve. Think of it like this. A cosmological constant is like a perfectly still lake, the same depth everywhere, never rising or falling. Quintessence is more like an ocean with tides. The water level changes, but slowly, over long periods. You wouldn't notice it from moment to moment, but across epochs of cosmic time, the energy density shifts. This field might even interact weakly with matter or dark matter. Most models assume dark energy is completely separate, affecting only the expansion of space itself. But maybe there's a subtle coupling, an influence so faint that we haven't detected it yet. Quintessence could be shaped by the distribution of matter, or could shape how matter clumps together, creating feedback loops across cosmic time that we're only beginning to understand. The appeal of quintessence is that it's more flexible than a pure constant. If observations show that dark energy's strength has changed over cosmic history, quintessence could explain that. A cosmological constant couldn't. Constants don't vary. That's kind of their whole thing. But there's a darker possibility. Some theories describe something called phantom energy. This is dark energy that doesn't just stay constant or slowly change. It grows stronger over time. Accelerating acceleration, if you will. The universe expanding faster and faster, with the rate of expansion itself increasing. If phantom energy is real, acceleration becomes unstoppable. It intensifies. At first, the effects are subtle, barely distinguishable from a cosmological constant. But given enough time, phantom energy leads to the Big Rip, cosmology's most violent ending. Here's how it would unfold. Right now, dark energy dominates on the largest scales, but gravity still holds galaxies together, still binds stars to their planets, still keeps your atoms from drifting apart. But if dark energy keeps strengthening, eventually it overcomes gravity on smaller and smaller scales. First, billions of years from now, galaxy clusters would dissolve. The galaxies within them would drift apart as space between them expands too fast for gravity to hold them together. The clusters that took billions of years to form would simply come undone, their galaxies scattering like leaves in an ever-strengthening wind. Then individual galaxies would break apart, stars scattering into the void. Then solar systems would disintegrate, planets torn from their orbits. The Earth would drift away from the Sun, not because anything pushed it, but because space itself would be expanding too fast for gravity to maintain the orbit. As phantom energy continues to grow stronger, even smaller structures would fail. Stars themselves would be ripped apart, their material flung into space. Then planets would shatter. Then, in the final moments before the big rip, molecules would be torn apart. Then atoms. Then atomic nuclei themselves. Space itself would be expanding so violently that nothing could remain intact. The universe wouldn't fade quietly into darkness. It would tear itself into subatomic shreds. Current evidence suggests this probably won't happen. Probably. The observations are more consistent with a cosmological constant or quintessence that doesn't strengthen significantly, but we haven't ruled it out completely. The possibility exists, lurking at the edges of our uncertainty, like an unwelcome thought you can't quite dismiss. On the opposite end, some models predict dark energy could weaken over time, a slow fade instead of a catastrophic strengthening. In this scenario, acceleration would gradually diminish, cosmic expansion eventually slowing again. The universe would still expand forever, but gently, asymptotically approaching some final state rather than ripping itself apart. A quiet ending instead of a violent one. Each of these theories, constant dark energy, quintessence, phantom energy, fading energy, predicts subtle differences in how expansion changes over cosmic time. The differences are small, requiring precise measurements across billions of years of cosmic history, but they're there. If we can measure the expansion rate at different epochs with enough accuracy, we can distinguish between these possibilities. That's what makes this solvable, at least in principle. Dark energy might be mysterious, but it's not completely beyond reach. It leaves signatures in how the universe expands, how structures form, how light travels across cosmic distances. We can observe those signatures. We can compare observations to predictions. We can test which model fits best. The problem is that all the models fit pretty well. Current observations can't definitively rule out quintessence or phantom energy. The cosmological constant remains the simplest explanation. Occam's razor favours it. But simplicity isn't proof. Nature isn't obligated to choose the simplest option. Sometimes the universe is more complicated than we'd like it to be. So we're left with multiple possibilities, each viable, each consistent with what we've measured so far. Dark energy could be constant, unchanging, eternal, or it could be dynamic, evolving, heading towards some unknown future state. We observe the acceleration, we measure its current strength, but we don't yet know its nature or its fate. And that uncertainty makes all the difference. If dark energy is constant, the universe will expand forever at an ever-increasing rate, eventually becoming cold and empty but never violent. If it's phantom energy, everything ends in the big rip. If it fades, the universe might eventually coast to a gentler fate. 3 different endings to the same story, and we're still trying to figure out which one we're living. Here's an uncomfortable thought. What if we're inventing dark energy to fix a problem that doesn't actually exist? What if the universe isn't full of mysterious invisible energy? What if gravity just works differently than we think? This is the intellectually honest alternative. Maybe we don't need dark energy at all. Maybe Einstein's equations, which work beautifully for solar systems and galaxies, need adjustment when applied to the scale of the entire universe. Perhaps gravity behaves differently across billions of light years. Not wrong exactly, just incomplete. Many physicists find this appealing. It's elegant in its way. No mysterious new substance filling space. No energy we can't detect or explain. Just refined understanding of gravity itself. We wouldn't be adding something to the universe. We'd be correcting our equations about how the universe behaves. Think about the history of physics. Newton's gravity worked perfectly for centuries, explaining everything from falling apples to planetary orbits. Then Einstein came along and showed that Newton's equations were approximations. They worked fine at everyday scales, but needed refinement when dealing with extreme situations, strong gravity, high speeds, cosmic distances. Einstein's general relativity replaced Newton's gravity, not because Newton was wrong, but because his equations needed extension. So maybe we're in a similar position now. Einstein's equations work perfectly for everything we've tested them on: black holes, gravitational waves, the bending of light around massive objects, all confirmed. But perhaps at the scale of the entire observable universe, general relativity needs its own correction. Maybe there's a regime where Einstein's equations, like Newton's before them, turn out to be excellent approximations of something deeper. This spawned a whole field of modified gravity theories, ideas with names like FR gravity, where the equations get tweaked by making the curvature of space work slightly differently, or theories involving extra dimensions beyond the 3 of space and 1 of time that we experience. In some models, gravity leaks into these hidden dimensions at cosmic scales, making it appear weaker than it should be. There's even a proposal called emergent gravity, suggesting that gravity isn't fundamental at all, but emerges from quantum entanglement between particles. In this view, what we call gravity is a collective effect arising from deeper quantum connections, and those connections might behave differently on cosmic scales than they do locally. These theories attempt to reproduce cosmic acceleration without inventing new energy. They try to explain why the universe is speeding up by changing the rules of gravity itself. And that's genuinely elegant. One modification, one adjustment to our understanding of space-time, and suddenly you don't need to fill 68% of the universe with something invisible. But there's a persistent problem. Every modified gravity theory proposed so far fails observational tests. Not all of them, not dramatically, but enough to cast doubt. The data keeps favoring dark energy. The patterns in the cosmic microwave background, the distribution of galaxies, the way light bends around massive structures, all of these observations fit better with a cosmological constant than with modified gravity. It's frustrating, actually. Modified gravity should work. It feels like it should work. The vacuum catastrophe is so severe, our predictions off by 120 orders of magnitude, that modifying gravity seems more reasonable than accepting we understand energy that poorly. But nature doesn't care what seems reasonable. Nature just is. Some modified gravity theories can mimic dark energy's effect on cosmic expansion, but fail when you look at how structures form over time. Others match structure formation but predict the wrong expansion history. Getting everything right simultaneously turns out to be remarkably difficult. The cosmological constant, for all its mysterious nature, fits all the observations with a single parameter. Modified gravity theories typically need multiple adjustments, and even then they struggle. There's also the problem of gravitational waves. In 2015, we detected them directly for the first time, ripples in space-time from colliding black holes. In 2017, we detected gravitational waves from colliding neutron stars, and also saw the light from the same event. This gave us an incredibly powerful test. If gravity is modified on cosmic scales, gravitational waves should travel at a different speed than light. They don't. They travel at exactly the speed of light, to within 1 part in a quadrillion. That single observation ruled out vast categories of modified gravity theories. Any theory that predicts gravitational waves should move faster or slower than light got eliminated by that one measurement. It was elegant and devastating. So modified gravity theories keep getting proposed, and observations keep narrowing the possibilities. The space for viable alternatives gets smaller with each new dataset. Maybe there's still a version that works, some clever modification we haven't thought of yet. But right now, the evidence keeps pointing back to dark energy, real substance filling space, not modified gravity, but something genuinely new in the universe. Still, the question remains open. The vacuum catastrophe is so severe that many scientists keep searching for gravitational alternatives. It's hard to accept that we understand energy so poorly. It's hard to believe the universe is 68% composed of something we can't detect, can't explain, and can't calculate correctly. Modified gravity at least offers a path where we're not fundamentally ignorant, just incomplete. But incomplete and ignorant might amount to the same thing in practice. Whether we're missing a correction to gravity or missing an understanding of vacuum energy, we're still missing something fundamental. The universe is accelerating. We observe it clearly. Whether that acceleration comes from energy filling space or from gravity behaving unexpectedly, we don't yet fully understand the cosmos we inhabit. The evidence points toward dark energy. The simplicity of the cosmological constant, despite our inability to calculate it, fits observations better than any modified gravity theory proposed so far. But the question isn't completely settled. Science stays open to alternatives. Maybe tomorrow someone will propose a modified gravity theory that fits everything perfectly. Maybe we'll discover that Einstein's equations, like Newton's before them, are approximations waiting for their next refinement. Until then, we're left with dark energy, mysterious, incalculable, but observationally supported. The universe filled with something we don't understand, pushing everything apart. So we have this theory about dark energy. We observe acceleration, we propose explanations. But how do we actually know? How do we build a case for something invisible that we can't detect directly? The evidence comes from multiple directions, different observations that all point to the same conclusion. It's like assembling a jigsaw puzzle where each piece comes from a different box, but somehow they all fit together to form the same picture. That convergence is what makes the case compelling. One of the most important pieces comes from the cosmic microwave background. This is ancient light, released when the universe was just 380,000 years old. Before that moment, the universe was too hot for atoms to exist. Electrons and protons floated free in a dense plasma that was completely opaque to light. Photons couldn't travel more than a short distance before scattering off a charged particle. The universe was bright but opaque, like being inside a luminous fog. Then the universe cooled enough for electrons and protons to combine into hydrogen atoms. Suddenly the plasma cleared. Light could travel freely for the first time, and that light has been traveling ever since, stretched and cooled by cosmic expansion, until today it reaches us as microwave radiation from every direction in the sky. When we map this radiation precisely, we see tiny temperature variations. Some patches are slightly warmer, some slightly cooler, with differences of only about 1 part in 100,000. These aren't random fluctuations, they're patterns. Maps of density variations in the early universe, seeds that eventually grew into galaxies and galaxy clusters over billions of years. The patterns tell us an enormous amount about the universe's composition. Think of it like reading tree rings. Each ring contains information about that year's growing conditions, temperature, rainfall, all encoded in the width and density of the wood. The cosmic microwave background works similarly. Those temperature patterns encode information about what the universe is made of, written in the structure of space itself. By analysing those tiny variations, their size, their distribution, how they correlate across different angular scales, cosmologists can determine the universe's composition with startling precision. The result is consistent across multiple independent analysis methods, different teams using different techniques, about 68% dark energy, about 27% dark matter, and only about 5% ordinary matter, the stuff that makes up stars, planets, and us. Dark energy isn't just present, it dominates. It's the single largest component of reality, more than twice as much dark energy as dark matter, more than 10 times as much as all the atoms in existence. Most of what the universe is made of is the thing pushing it apart. We are, quite literally, a tiny minority in a universe that prefers emptiness. The cosmic microwave background tells us something else crucial. Without dark energy, the observed geometry of the universe wouldn't be flat. Let me explain what that means. General relativity allows the universe to have different shapes. It could curve back on itself like the surface of a sphere, a closed universe where travelling far enough in one direction would eventually bring you back to where you started. Or it could curve the opposite way, like a saddle, an open universe that extends infinitely in all directions. Or it could be flat, with parallel lines staying parallel forever, just like Euclidean geometry teaches. The cosmic microwave background patterns reveal which geometry we actually have. They act like a cosmic surveying tool, measuring the large-scale curvature of space itself. The way temperature variations correlate at different angular separations depend on the geometry, different patterns for different curvatures. And the answer is flat, remarkably, precisely flat. The universe has zero curvature, at least within our measurement precision. But here's the thing. For the universe to be flat, it needs to have a very specific total energy density. Too little, and it curves open like a saddle. Too much, and it curves closed like a sphere. The amount of matter we observe, ordinary matter plus dark matter, isn't enough. It's only about 32% of what's needed. To make the geometry flat, we need the other 68%. We need dark energy. It's not that we invented dark energy to explain flatness. We discovered acceleration first, independently, from supernovae. But when we measured the geometry of the universe, it fit perfectly with the amount of dark energy needed to explain acceleration. Two completely different observations pointing to the same invisible substance. That's when scientists really started paying attention. Then there's the evidence from galaxy surveys. By mapping billions of galaxies and measuring their positions in 3 dimensions, astronomers can trace how cosmic structure has evolved over time. Remember, looking farther away means looking back in time. Distant galaxies show us the universe as it was billions of years ago. The patterns reveal something interesting. Structure grows more slowly than we'd expect from gravity alone. Galaxies cluster together, forming the cosmic web of filaments and voids, but not as enthusiastically as they should if only matter's gravity were at work. Dark energy counteracts gravity on the larger scales. It doesn't pull things together, it pushes them apart, and that gentle push slows down the formation of cosmic structures. Without dark energy, we'd see denser clustering, faster structure growth, a universe more clumped than the one we observe. With dark energy, the predictions match reality. The cosmic web of galaxies, the distribution of clusters, the growth of structure over billions of years, all consistent with a universe dominated by dark energy. There's another piece of evidence called baryon acoustic oscillations. These are frozen sound waves from the early universe, imprinted in the distribution of galaxies. Yes, sound waves. Before atoms formed, The universe was filled with that hot plasma, electrons, protons, photons, all interacting intensely. Pressure waves moved through this plasma at about half the speed of light, just like sound waves move through air, only much faster. When atoms formed and the plasma cleared, these waves froze in place. They left an imprint, a preferred scale in how matter clumps together. Today, billions of years later, galaxies are slightly more likely to be separated by a specific distance, about 500 million light-years, because of those ancient sound waves rippling through the infant universe. This distance serves as a cosmic ruler. We know how big those waves should be based on the physics of the early universe. By measuring how big they appear to us now, at different distances, and therefore different times in cosmic history, we can track how the universe has expanded. It's like measuring a ruler that's been stretched by cosmic expansion. If you know the ruler's original length, you can determine how much space has stretched. Baryon acoustic oscillations confirm the acceleration. They provide an independent check on the expansion history, and that history matches what we found from supernovae and the cosmic microwave background. Again, different methods, same conclusion. Dark energy exists, the universe is accelerating. The measurements agree. Every measurement technique has its uncertainties and potential systematic errors. Any single observation could potentially be wrong, but when multiple independent methods all point to the same answer, confidence grows. It's not just one observation that could be mistaken. It's many observations, using different telescopes, different wavelengths of light, different physical phenomena, all telling the same story. The cosmic microwave background says 68% dark energy. Galaxy clustering says the universe needs dark energy to match observations. Baryon acoustic oscillations confirm the expansion history. Supernovae show acceleration. The geometry of space requires dark energy to be flat. Each piece of evidence, standing alone, would be suggestive. Together, they're convincing. This is how science builds certainty, not from single observations, but from convergence. We're measuring something real, something invisible, something we don't understand, but something that's genuinely there. Dark energy isn't speculation or wishful thinking. It's an observational fact, even if it remains a theoretical mystery. We've built the case for its existence from multiple directions, and all the evidence points the same way. The universe is 68% something we can't see, can't touch, can't explain. And we know this is true not because of one observation, but because of many. The evidence mounts from every corner of cosmology, building a picture of a universe dominated by mystery. We live in a cosmos we're only beginning to understand. So we've measured dark energy from multiple directions, and all the evidence converges. Everything points to the same answer, except when it doesn't. There's a problem, a significant one. When astronomers measure how fast the universe is expanding right now, using local observations of relatively nearby objects, they get one number. When they measure the expansion rate from the cosmic microwave background from the early universe, they get a different number, and the two don't agree. This disagreement is called the Hubble Tension. It's named after Edwin Hubble, the astronomer who discovered cosmic expansion in the first place. The tension is the polite scientific term for what amounts to a crisis. Two different methods for measuring the same thing are giving us incompatible answers. Let me explain how the local measurement works. Astronomers use what's called the distance ladder, a step-by-step method for measuring cosmic distances. The first step uses Cepheid variable stars that pulse with regular periods, brightening and dimming in predictable rhythms. There's a relationship between how fast a Cepheid pulses and how bright it actually is. Measure the pulse rate, and you know its true brightness. Compare that to how bright it appears, and you can calculate its distance. Using Cepheids, astronomers can measure distances to nearby galaxies with good precision. Then they look for type 1a supernovae in those same galaxies. Remember those? The exploding white dwarfs that shine with predictable brightness. Since we know the distance of the galaxy from Cepheids, we can calibrate exactly how bright those supernovae should appear at that distance. Then we look at more distant supernovae, far beyond where we can see individual Cepheids. We know how bright these supernovae should be based on our calibration. We measure how bright they appear, and from that we calculate their distances and how fast they're moving away from us. This tells us the expansion rate of the universe today. Using this distance ladder method, astronomers measure an expansion rate of about 73 kilometers per second per megaparsec. That means for every megaparsec of distance, about 3.26 million light-years, space is expanding at 73 kilometers per second. It's the current speed at which the universe is stretching. Now let's look at the other measurement. The cosmic microwave background gives us a snapshot of the universe when it was 380,000 years old. By analysing the patterns in that ancient light, cosmologists can determine all the parameters that describe the universe. How much matter, how much dark energy, how fast it was expanding then, and how those ingredients should make it expand over time. Using the best model we have, called lambda CDM, lambda for the cosmological constant, CDM for cold dark matter, they can calculate what the expansion rate should be today. The cosmic microwave background itself doesn't directly measure today's expansion rate. It measures the early universe, and then uses physics to predict what should happen over the next 13.8 billion years. That prediction gives an expansion rate of about 67 kilometers per second per megaparsec. Not 73, 67. The difference is about 9%. That might not sound like much. In everyday life, 9% is a rounding error. Your coffee cost 9% more than last year, and you barely notice. But in precision cosmology, where measurements are accurate to better than 1%, a 9% disagreement is enormous. It's statistically significant, far beyond what could be explained by measurement uncertainty. Both methods are extremely precise. The distance ladder measurement has been refined over decades with better telescopes, more Cepheids, more supernovae, improved calibration. The cosmic microwave background has been mapped by multiple satellites, WMAP, Planck, with extraordinary detail. Both teams know what they're doing. Both measurements are carefully checked and rechecked, and they don't agree. Here's what makes this truly unsettling. As both teams have improved their measurements, the disagreement hasn't gone away. It's gotten worse. More precise instruments, better calibration, larger data sets. None of this is making the two numbers converge. Instead, we're becoming more and more certain that they genuinely disagree. This isn't supposed to happen in precision cosmology. When you measure something two different ways, the results should agree if you're doing it right. If they don't agree at first, you look for systematic errors, refine your techniques, and eventually the numbers converge. That's how science works. Discrepancies get resolved. But this one isn't resolving. The tension has been around for years now, and it's not fading with better data. If anything, it's becoming more pronounced. We're measuring the same universe, the same expansion rate, but getting two different answers. Depending on how we look, it's like measuring your height with a tape measure and getting 6 feet, then measuring with a laser rangefinder and getting 5'8". Both instruments are precise. Both are carefully calibrated. They just disagree. Some astronomers think it's a calibration issue that will eventually be resolved. Maybe there's some subtle systematic error in the distance ladder. Maybe Cepheid stars don't all behave quite as predictably as we think. Maybe there's something about supernova brightness we haven't fully understood. These are reasonable concerns, and people are actively investigating them. But others suspect the tension could hint at new physics. Maybe dark energy isn't constant after all. Maybe it's been evolving over cosmic time in ways our current model doesn't account for. Or maybe there's something else in the universe we haven't discovered yet, some additional component that affects expansion in ways we don't understand. There are more exotic possibilities too. Maybe the cosmic microwave background measurement is correct for the average expansion rate across the whole universe, but we live in a region that's expanding slightly faster than average, a kind of cosmic void where density is lower and acceleration is higher. Or maybe general relativity needs modification in subtle ways that only show up when comparing local and cosmic measurements. The tension persists regardless. Two numbers that should be the same, measured with extraordinary precision, stubbornly refusing to agree. It's become one of the most pressing problems in modern cosmology. Conferences are held about it, papers are published trying to explain it. Theorists propose new models, observers refine measurements, and the disagreement remains. What makes this particularly frustrating is that we can't just average the two numbers and call it solved. They're measuring the same thing in fundamentally different ways, one looking at the universe now and working backward, the other looking at the early universe and working forward. If they disagree, something is wrong with our understanding. Either our measurements have undetected errors, or our model of how the universe evolves is incomplete. This is the kind of tension that can lead to breakthroughs. Historically, when precise measurements disagree, it often means we're missing something important. The orbit of Mercury didn't quite match Newton's predictions. That tension led to general relativity. The spectrum of black-body radiation didn't match classical physics. That tension led to quantum mechanics. Disagreements between careful measurements are often signposts pointing toward new understanding. Or sometimes they're just measurement errors that eventually get fixed. We don't know yet which this is. That's the uncomfortable part. We're living through the uncertainty, watching scientists work to resolve it, unable to know whether we're witnessing the prelude to a revolution or just a particularly stubborn systematic error. The Hubble tension has become a genuine crisis in cosmology. Not the kind of crisis where everything falls apart, but the kind where scientists realize they don't understand something they thought they did. We have two precise measurements of the same quantity, and they don't agree. That's uncomfortable. That suggests ignorance. And in science, discovering your ignorance is often the first step toward understanding. The tension might be telling us something important. Maybe dark energy isn't what we think it is. Maybe the universe is more complicated than our current model allows. Maybe we're on the verge of the next major revision in cosmology. Or maybe someone will find the systematic error everyone's been missing, and the two numbers will suddenly agree, and we'll all feel slightly foolish for worrying so much. But right now, the tension persists. The disagreement remains, and cosmologists are left with the uncomfortable knowledge that something about our picture of the universe doesn't quite add up. So, we have mysteries. The vacuum catastrophe, the Hubble tension, dark energy itself. But we're not just sitting around contemplating our ignorance. We're building telescopes, launching satellites, mapping the cosmos with unprecedented precision. The hunt for answers is happening right now, in real time, during our lifetimes. Multiple missions are currently underway or recently launched, all designed to probe dark energy from different angles. It's a coordinated effort across continents and space agencies, a global attempt to understand what makes up most of the universe. This isn't something we'll figure out eventually someday, in the distant future. It's happening now. The Vera Rubin Observatory sits on a mountaintop in Chile, currently being commissioned. When it begins full operations, it will survey the entire southern sky repeatedly, night after night for 10 years. Its camera is the largest ever built for astronomy, 3.2 billion pixels, capable of capturing an area of sky 40 times the size of the full moon in a single exposure. Think about that. 40 full moons worth of sky in one photograph. Every few nights, Rubin will photograph the entire visible southern sky. Over a decade, it will map billions of galaxies, tracking how they move, how they cluster, how cosmic structures evolve over time. The goal is to trace dark energy's influence across the history of the universe. If dark energy has changed over time, if it's quintessence rather than a constant, Rubin should be able to detect that change. The telescope will also observe supernovae, thousands of them, perhaps tens of thousands, each one a data point in mapping cosmic expansion. More supernovae means better statistics, tighter constraints on how the expansion rate has changed over billions of years. Rubin won't just confirm what we already know. It's designed to find deviations, subtle changes, any hint that dark energy behaves differently than a simple cosmological constant predicts. In space, the Euclid telescope launched in 2023. It's orbiting the Sun about 1 million miles from Earth at a location called the second Lagrange point, where it can maintain a stable position relative to Earth and Sun. From this vantage point, away from Earth's atmospheric distortions, Euclid is mapping the geometry of the universe with unprecedented precision. It observes billions of galaxies across more than a third of the sky, measuring their shapes and distances. Why shapes? Because dark energy affects how space curves, and that curvature distorts the apparent shapes of distant galaxies through a phenomenon called weak gravitational lensing. Gravity bends light. As light from distant galaxies travels through space, it passes through regions of varying density, and those variations slightly distort the galaxy's apparent shape. The distortion is tiny. You couldn't see it by looking at a single galaxy, but measure billions of galaxies, and the statistical pattern becomes clear. By measuring these tiny distortions across billions of galaxies, Euclid can map the geometry of spacetime itself. It's using galaxy shapes as probes of cosmic geometry, seeing how dark energy shapes the universe on the larger scales. The telescope also measures baryon acoustic oscillations, those frozen sound waves we talked about earlier. By observing them at different cosmic epochs across different distances, Euclid traces how dark energy has influenced the expansion over time. Multiple techniques, multiple measurements, all designed to constrain dark energy's properties from different angles. Then there's the Nancy Grace Roman Space Telescope, scheduled to launch in the next few years. Named after NASA's first chief of astronomy, who fought to make space telescopes a reality, Roman will have a field of view 100 times larger than Hubble's. It's designed specifically to investigate dark energy through multiple independent methods. Roman will observe Type I supernovae, adding to the catalogue that first revealed acceleration. But it will also map millions of galaxies, measuring weak gravitational lensing like Euclid. It will observe baryon acoustic oscillations. It will study galaxy clusters and how they evolve over cosmic time. Each method provides a different way to measure dark energy, and having multiple measurements helps identify and eliminate systematic errors. The redundancy is intentional. If all methods agree, confidence grows. If they disagree, that's information too. It tells us something about our assumptions or our measurements. Roman is built to cross-check itself, to verify results through independent techniques, to make sure we're not being fooled by some subtle bias in any single method. It's a telescope designed with skepticism built in. On the ground, the Dark Energy Spectroscopic Instrument, DESI, is already operating. It's installed on a telescope in Arizona, and it's creating the most detailed three-dimensional map of the universe ever made. DESI can observe 5,000 galaxies simultaneously, measuring their distances and mapping their positions in space. 5,000 spectra at once, each one revealing how fast a galaxy is moving away from us. Over 5 years, DESI will map more than 40 million galaxies and quasars, 40 million three-dimensional positions, each one a point in the cosmic web. This creates a map showing how matter clusters across billions of light years and billions of years of cosmic time. From this map, astronomers can measure how dark energy has influenced structure formation and cosmic expansion throughout the universe's history. DESI is particularly good at detecting baryon acoustic oscillations. Remember, these are the standard ruler. We know their physical size from the physics of the early universe, so measuring their apparent size tells us the expansion history. With 40 million galaxies, DESI can measure these oscillations with extraordinary precision at many different epochs, tracing how the expansion rate has changed over time. All these missions are designed to distinguish between different dark energy models. Is it constant? Is it quintessence, slowly evolving? Is it phantom energy, growing stronger? Each possibility predicts slightly different patterns in how the universe expands, how structures form, how light travels across cosmic distances. The differences are subtle. That's why we need such precise measurements from multiple independent missions. A single observation might not distinguish between a cosmological constant and slowly changing quintessence, but combine observations from Rubin, Euclid, Roman, and DESI, and the picture becomes clearer. The models make different predictions. The data will show which predictions match reality. These missions are also designed to address the Hubble tension. By measuring the expansion rate using multiple methods across multiple distances, they should help identify where the disagreement comes from. Is it a problem with how we calibrate distances? Is it telling us dark energy changes over time? Is it revealing physics we don't yet understand? The answer is in the data, and the data is being collected right now. Within this decade, we should have answers. Not complete answers. Dark energy will probably remain mysterious in some fundamental ways, but better answers. We'll know whether the cosmological constant fits the data or whether we need something more complex. We'll have tighter constraints on how dark energy behaves over cosmic time. We might even resolve the Hubble tension one way or another. Or the mystery might deepen. That's also possible. Every time we've looked at the universe more carefully, we've found it stranger than we expected. Maybe these new missions will raise more questions than they answer. Maybe they'll reveal that our current models are even more wrong than we thought. Discovery works both ways. That's the nature of exploration. You don't know what you'll find until you look. Sometimes you find answers. Sometimes you find deeper mysteries. Both outcomes advance understanding. Even discovering how wrong you were is progress, because it tells you where to look next. The data is coming in now. DESI is operating, mapping galaxies every clear night. Euclid is collecting observations, building its catalogue of billions of galaxies. Rubin will start its survey soon, beginning its decade-long watch of the southern sky. Within our lifetimes, probably within the next decade, we'll have the most comprehensive picture of dark energy ever assembled. Multiple missions, multiple methods, millions of observations, all focused on the same question. What is dark energy, and what will it do to the universe? This is the golden age of dark energy research. The technology exists. The missions are funded and operational. The observations are being made right now, tonight, as you listen to this. Telescopes on Earth and in space are capturing photons that travelled billions of years to reach us, each one carrying information about how the universe expands. We might finally understand the force that dominates the cosmos, or we might discover that the mystery is even deeper than we imagined. Either way, we're about to find out. The suspense isn't hypothetical, it's actually happening in real time, as data accumulates and scientists analyze what the universe is telling us. The hunt for answers isn't someday, it's now, and whatever we find, whether it confirms our models or shatters them completely, will reshape our understanding of reality itself. So, dark energy exists. It's accelerating the universe. And that acceleration has consequences. Not immediate consequences. Nothing happens overnight on cosmic timescales. But inevitable ones. The universe is changing, slowly but irreversibly becoming something different with each passing billion years. Right now, as expansion accelerates, galaxies drift farther apart with each passing moment. The space between them is growing, not because the galaxies themselves are moving, but because space itself is stretching, carrying them along, and as that distance grows, the rate of separation increases. Acceleration means the farther apart things are, the faster they move away from each other. This has a strange consequence. Our local group of galaxies, the Milky Way, Andromeda, and about 50 smaller galaxies bound together by gravity, will remain visible. Gravity holds us together, overcoming the expansion. In fact, the Milky Way and Andromeda are currently moving toward each other, destined to merge in a few billion years into one enormous elliptical galaxy. Our local neighborhood will stay intact, bound by mutual gravity that's stronger than dark energy's push on these scales. But beyond our local group, everything else is drifting away. And in billions of years, as acceleration continues, only our merged galaxy cluster will remain gravitationally bound and visible. Everything else will slip beyond reach. Future astronomers in that distant era, if any exist, will look out at the night sky and see only their local stars, with nothing but darkness beyond. Distant galaxies are already moving away from us. Some are receding so fast that their light, stretched by expansion, has been redshifted into infrared and beyond. But we can still see them. We can still detect their light, still map their position, still know they're there. That will change. As expansion accelerates, those distant galaxies will eventually cross what's called the cosmic horizon. This isn't a physical boundary. It's more like an information barrier. Once a galaxy crosses the horizon, its light will never reach us again, no matter how long we wait. The space between us will be expanding faster than light can travel across it. This is one of the strange things relativity allows. Nothing can move through space faster than light. That's still true, but space itself can expand at any rate. There's no speed limit on the stretching of space-time. So while galaxies aren't moving faster than light through space, the space between us and them can grow faster than light can cross it. When that happens, the galaxy becomes causally disconnected from us. It still exists out there somewhere, but it's beyond reach forever. No signal will ever arrive. No light will ever make the journey. It's not hidden. It's gone from our observable universe, separated by expansion we can't overcome. One by one, distant galaxies will cross this horizon and disappear. Not all at once, but gradually, over trillions of years. The night sky will grow emptier and darker as each distant light winks out, not because those galaxies died, but because the universe has stretched the space between us beyond the point where light can traverse it. Think about what this means for distant civilizations, if they exist. Right now, we could theoretically send a signal to nearby galaxies, and given enough time, it would reach them. Light travels at finite speed, but it travels. Send a message toward Andromeda, and in 2.5 million years, it would arrive. But galaxies beyond a certain distance are already receding so fast that even light sent toward them today will never arrive. We've already lost the ability to communicate with most of the universe. And as acceleration continues, that boundary gets closer. Galaxies that we could theoretically reach today will be unreachable tomorrow in cosmic terms. The observable universe is shrinking, not in the sense that space is contracting, but in the sense that more and more of space is expanding away from us faster than light can connect us. Meanwhile, stars continue their life cycles. They burn, they age, they die. Star formation depends on cold gas clouds collapsing under gravity. But as the universe expands and galaxies drift apart, the gas needed to form new stars spreads thinner. Star formation slows. Not immediately. Our galaxy will make stars for tens of billions of years yet, but eventually, our galaxy will continue making stars for a long time. There's plenty of gas, and we keep recycling material from dying stars. When a star explodes or sheds its outer layers, that enriched material gets incorporated into new stars. But eventually, the gas runs out or becomes too dispersed. New stars stop forming. The universe enters an era dominated by the stars that already exist, slowly burning through their remaining fuel. Stars aren't eternal. The smallest, most miserly red dwarfs might burn for trillions of years, but they too will eventually exhaust their fuel. Medium-sized stars like the Sun last billions of years. Massive stars burn through their fuel in mere millions. One by one, over unfathomable stretches of time, the stars go out. First the massive ones exploding as supernovae or collapsing into black holes. Then the medium-sized ones swelling into red giants before shedding their outer layers and fading to white dwarfs, dim embers cooling slowly in the dark. Finally, after trillions upon trillions of years, even the smallest red dwarfs exhaust their fuel and fade. The universe enters what cosmologists call the dark era. No more star formation. The existing stars have all died or faded to black dwarfs, cold, dark remnants that no longer shine. Galaxies become graveyards filled with stellar corpses, white dwarfs, neutron stars, black holes, all drifting in darkness. This isn't a quick process. We're talking timescales that make the current age of the universe, 13.8 billion years, seem like an eye blink. The dark era begins perhaps 100 trillion years from now. That's more than 7,000 times longer than the universe has currently existed. The stars will shine for a very, very long time before the darkness comes. But it comes eventually. The universe grows cold and dark and nearly silent. No more fusion reactions lighting up the night. No more galaxies visible beyond our local cluster. No more new stars being born. Just remnants, cooling slowly, drifting through expanding space that grows emptier with each passing eon. This ending has a name, the Big Freeze, sometimes called the heat death. Not because everything freezes solid, but because the universe runs out of usable energy. Heat spreads out, entropy increases, and everything approaches the same cold temperature, slightly above absolute zero. No more temperature differences means no more engines can run, no more processes can extract energy, no more change is possible. It's not violent. There's no catastrophic explosion, no tearing of space, no final dramatic moment. Just a slow, gentle fading. The universe doesn't end with a bang or even a whimper. It just gets quieter and colder and emptier forever. This is what dark energy gives us if it remains constant. An eternal expansion, an endless dilution, a universe that doesn't die so much as it just spreads out. Every structure that gravity can hold together stays bound. Our local galaxy cluster, orbiting stellar remnants, maybe even some planets still circling dead stars. But everything beyond our gravitationally bound region recedes beyond reach, and eventually the lights go out. It's a lonely ending, not terrifying exactly, just lonely. The universe becomes a collection of isolated islands, each one drifting alone through expanding darkness, unable to see or reach any of the others. Each island a small cluster of dead stars and cold planets, separated from all other islands by gulfs of space that grow wider every moment. And yet there's something almost peaceful about it. The universe doesn't tear itself apart. It doesn't collapse in fire. It just gradually runs down like a clock slowly unwinding, tick by tick, until finally the mechanism stops and everything is still. This is the fate dark energy appears to have chosen for us. A slow fade rather than a dramatic conclusion. An eternal expansion rather than a final collapse. The universe doesn't end. It just becomes very, very quiet. So, dark energy dominates the universe now. About 68% of everything, driving the acceleration we observe. But here's something strange. It hasn't always dominated, and that timing raises uncomfortable questions. For the first 9 billion years after the Big Bang, matter was in charge. Dark matter and ordinary matter together made up most of the universe's energy density, and their gravity dominated cosmic evolution. Dark energy was there too, with the same value it has today, if it's truly constant. But it was overwhelmed by everything else. Matter was denser, more concentrated, and its gravitational influence shaped how the universe expanded and how structures formed. But as the universe expanded, matter diluted, spread the same amount of matter across a larger volume, and its density drops. Meanwhile, dark energy stayed constant, same energy density per cubic meter, regardless of how much the universe grew. Eventually, around 5 or 6 billion years ago, the densities crossed. Dark energy's density overtook matter's density, and acceleration began. The transition happened relatively recently in cosmic terms. The universe is 13.8 billion years old. For the first 9 billion years, matter dominated. For the next trillion years or more, dark energy will dominate. And we happen to live right at the transition between these two eras, just a few billion years after the crossover. This seems suspicious, cosmically suspicious. Why do we observe the universe just when dark energy is becoming important? The universe will exist for an unfathomably long time, most of it dominated by dark energy, spreading ever emptier and colder. But we happen to be here right at the brief moment when matter and dark energy are roughly comparable, when the transition is still recent enough to observe. It's like arriving at a theatre exactly during intermission. Possible, certainly, but you'd wonder about the timing. The play runs for hours. Intermission lasts 15 minutes. What are the odds you showed up precisely then? Physicists call this the coincidence problem, not because it's definitely a coincidence, but because the timing seems too convenient to be random. We exist during the one epoch when both matter and dark energy are significant, when the universe is transitioning from deceleration to acceleration, when both components are visible in our observations. Some scientists invoke the anthropic principle as an explanation. We observe this era because only in this era could observers exist. Too early in cosmic history and heavy elements are scarce. Not enough supernovae have enriched the universe with carbon, oxygen, iron. Stars are forming rapidly, but planets like Earth haven't had time to form and evolve complex life. Too late, and the universe is too spread out. Galaxies have drifted beyond sight. Star formation has ceased. The resources needed for life, dense molecular clouds, active stellar systems, energy gradients no longer exist in abundance. The universe becomes inhospitable to complexity. We live now because now is when complex life becomes possible. The timing isn't coincidental, it's necessary. We couldn't observe the matter-dominated era because we wouldn't exist yet. We won't observe the far future dark energy-dominated era because we'll be long gone. We're here now because now is the window when observers can exist. That explanation feels unsatisfying to many physicists. It's not wrong exactly, but it doesn't really explain anything. It just says, of course you're here now, because if you weren't, you wouldn't be asking the question. Which is true, but somehow circular. It doesn't tell us why the universe is set up this way to begin with. Then there's the fine-tuning problem, which is related but even more unsettling. Dark energy's strength is suspiciously perfect. If it were just 10 times stronger than we observe, galaxies would never have formed. The acceleration would have started too early, pulling matter apart before gravity could gather it into galaxies and stars. A universe with dark energy 10 times stronger would still have matter and radiation, and the Big Bang and expansion. But that expansion would accelerate so quickly that density fluctuations couldn't grow. The slight variations in density that eventually became galaxies would be stretched apart before they could collapse. No galaxies means no stars. No stars means no planets. No planets means no us. If dark energy were 10 times weaker, the universe might have already recollapsed. A weaker cosmological constant means matter's gravity becomes relatively stronger. Instead of coasting to eternal expansion, the universe might slow, stop, and fall back on itself in a big crunch. Or it might expand forever but without acceleration, which changes the geometry and evolution of cosmic structure in ways that might not allow complex structures to form. The actual value of dark energy sits in a narrow range, strong enough that the universe expands forever, weak enough that galaxies had time to form before acceleration began dominating. It's Goldilocks fine-tuning. Not too strong, not too weak, but just right for a universe that contains galaxies and stars and observers. This demands explanation. Either we're incredibly lucky, or there's a reason the value is what it is. Luck seems unsatisfying when you're dealing with a parameter that determines whether complexity can exist. 1 part in 10 seems like narrow odds for the entire possibility of structure in the universe. One possible answer is pure chance. The universe has the parameters it has, and we exist to observe them because these parameters allow existence. If they were different, we wouldn't be here to wonder about it. This is the anthropic principle again, extended to fundamental constants. The universe appears fine-tuned for life, because only a fine-tuned universe can produce beings to notice the fine-tuning. Another answer invokes the multiverse hypothesis. Maybe our universe is one of many, perhaps infinitely many, each with different fundamental constants. Most of those universes have dark energy values that don't allow complexity. Too strong and nothing clumps. Too weak and everything collapses. But in a tiny fraction of universes, the value falls in the habitable range. We necessarily find ourselves in one of those rare universes, because only those universes have observers. This doesn't make our universe less special exactly. It just means we're in the cosmically habitable subset of an enormous multiverse, most of which is inhospitable. We're in the one in whatever universe where the parameters allow galaxies and stars and planets and life. Not because we're special, but because we literally couldn't exist in any of the others. The multiverse idea is controversial. It's not directly testable. We can't observe other universes. So some physicists argue it's not science. Others counter that it's a natural prediction of certain theories like eternal inflation. and that we should take those predictions seriously even if we can't verify them observationally. Or maybe we're missing something. Maybe there's deeper physics that explains why the cosmological constant has the value it does. Some principle we haven't discovered yet, some symmetry or mechanism that forces dark energy to be this strength rather than any other. The value wouldn't be coincidental or fine-tuned. It would be necessary, determined by laws we don't yet understand. That would be the most satisfying answer intellectually. Not, we got lucky, or we're in one universe among many, but the value must be what it is because of principles we've now discovered. It would transform the coincidence problem from mystery into understanding. But we don't have that answer yet. We observe the value, we notice the timing. We recognize both seem suspiciously convenient, and we're left with multiple possible explanations, none completely satisfying, none definitively proven. The universe could be fine-tuned by chance, or by necessity through laws we haven't found, or we might be one universe among countless others selected by the anthropic filter of existence itself. Each explanation has advocates and problems. What we know for certain is this. Dark energy has exactly the right strength to allow galaxies to form before acceleration dominated, and we exist in exactly the right epoch to observe both matter and dark energy playing important roles. Whether that's profound coincidence, anthropic necessity, multiverse statistics, or hidden physics remains one of cosmology's deepest puzzles. The universe is fine-tuned for complexity, fine-tuned for us in ways we can measure but don't yet fully understand, and we're here now at just the right time to notice. Right now, as you listen to this, dark energy surrounds you. It's invisible but omnipresent. It fills every cubic centimetre of space, in this room, in the air between you and the walls, in the space between atoms in your body. Every cubic metre contains it. You can't feel it. No instrument can directly detect it. But it's there, gently stretching space-time itself. The ultimate invisible presence. While dark matter holds galaxies together through its gravity, dark energy pushes the entire universe apart through its anti-gravity. Two invisible forces in constant opposition, and we, visible matter, conscious observers, exist in the tension between them. We are the bright dust caught between dark forces we barely understand. Dark energy is sometimes called anti-gravity, which isn't quite right, but captures something true. Gravity pulls, dark energy pushes. Gravity tries to bring things together. Dark energy drives them apart. They're opposites in effect, working against each other on cosmic scales, and for now, on the largest scales, dark energy is winning. But it's not a violent force. It doesn't buffet or tear. It stretches space silently and evenly, without wind or sound or any physical sensation we could detect. You can't shield yourself from it. You can't build a wall to keep it out. It permeates everything, everywhere, always. The energy of nothing, present in every moment. Think about what that means. The fabric of reality itself contains energy. Empty space isn't empty. The vacuum has properties, has substance, has the power to shape the entire cosmos. This might be the strangest thing physics has ever discovered, that nothingness can have power, that the absence of matter can drive the fate of everything. Dark energy is both infinite in extent and intimate in presence. It stretches across the entire observable universe, filling every corner, present in voids between galaxy superclusters and in the space between electrons and nuclei. No distance too vast, no space too small. It's everywhere equally uniformly distributed, unchanging and eternal, if the cosmological constant is correct. What we're describing is a property of space-time itself, not something moving through space, but something inherent in the structure of space. Like how a ruler has length, space-time has energy density. It's built in, fundamental, unavoidable. You can't remove dark energy from the universe any more than you can remove length from a line. This is what makes it so hard to understand. We're used to energy as something that does things, fuel that burns, electricity that flows, kinetic energy of moving objects. But dark energy just sits there, filling space, pushing gently but inexorably. It doesn't do anything except exist, and by existing, it shapes the universe. Astronomers may never fully understand it. We might measure its effects precisely, constrain its properties, determine whether it's constant or evolving. But the fundamental question, why does it exist? Why does it have the value it does? Might remain forever beyond our reach. Some mysteries might be too deep for human physics to penetrate. Yet through dark energy we glimpse something profound about the nature of existence itself. The universe prefers emptiness. Given enough time, dark energy wins and space becomes sparse, with matter diluted to near nothingness. The natural state of the cosmos isn't fullness but void. We live in a brief, dense moment, cosmically speaking. The universe's future is mostly empty space. We are a visible minority in a universe that prefers emptiness. Matter makes up only about 5% of everything. Dark matter adds another 27%. Together, all the stuff that actually does things, that clumps and clusters and forms structures, is outnumbered 2-to-1 by the force that pushes everything apart. We're the exception, not the rule. And we live in a brief moment between density and eternal separation. The universe was once much denser. In the first moments after the Big Bang, everything was compressed into an unimaginably small space. It's been expanding and diluting ever since. For a while, gravity slowed that expansion. Now dark energy accelerates it. Eventually, matter will spread so thin that for practical purposes the universe will be empty. This is our moment, right now. The brief span of cosmic time when matter is abundant enough to form complex structures, but not so compressed that conditions are too violent. When stars have manufactured enough heavy elements to make planets and life possible, but haven't all burned out yet. When galaxies are close enough to observe, but not so close they're colliding constantly. There's something strange about being conscious. Matter observing its own dispersal. We're made of atoms, hydrogen from the Big Bang, heavy elements from dead stars, and we've arranged ourselves into patterns complex enough to contemplate the cosmos. And what we observe is that everything is drifting apart, including eventually us. The universe that created us is slowly pulling itself to pieces. Both wonder and dread are appropriate responses to this knowledge. Wonder at the scale, at the elegance of dark energy's mathematical description, at the fact we've detected and measured something so subtle. Dread at the implications, at the loneliness of the universe's far future, at our own cosmic insignificance in the face of forces we can't control. But perhaps more than either, what we should feel is urgency, not panic. Nothing happens fast on cosmic timescales, but recognition that we exist in a privileged moment, a brief window when the universe is observable and comprehensible. Future civilizations, if they exist trillions of years from now, will see only their local cluster in an otherwise empty sky. They won't have access to the evidence we have. They might never discover cosmic expansion or dark energy. We have an obligation, in a sense, to understand while we can, to observe, to measure, to record, to comprehend as deeply as our physics allows. We're the universe becoming conscious of itself, at just the right moment to understand its own nature. That opportunity won't last forever. Science is humanity's response to cosmic mystery. We don't just wonder about dark energy. We build telescopes to measure it, satellites to map it, theories to explain it. We take the mystery and interrogate it with observation and mathematics until it yields whatever understanding is possible. That might be the most remarkable thing our species does. 68% of everything. That's what dark energy represents. More than 2/3 of the universe is this invisible field pushing everything apart, determining the fate of all existence. Not dark matter holding things together, but dark energy pulling them apart. The repulsive force that will win in the end. And yet for all its power, dark energy works quietly. No explosions, no violence, no drama. Just patient, relentless stretching of space itself. Acceleration so gentle you can't measure it in a human lifetime, only across billions of years. Power without force, influence without presence, the energy that shapes everything while touching nothing. The universe breathes in a way, not like lungs filling and emptying, but like a single eternal exhalation, expanding, spreading, stretching with each cosmic breath. And in that quiet rhythm we find both wonder and the knowledge that even emptiness has power. Dark energy surrounds you right now. It filled the space where you are before you were there. It will fill that space after you're gone. It's the energy of the vacuum, the property of nothingness, the force that will ultimately determine the fate of everything. And it does all this silently, invisibly, without any sign you could perceive. This is the strange universe we inhabit, dominated by something we can't see, pushed apart by something we don't understand, heading toward a future of increasing emptiness and isolation. And yet, we're here, conscious matter in temporary form, able to observe and measure and comprehend this cosmic strangeness. That we exist at all is improbable. That we exist now, during the brief era when both matter and dark energy are significant, is doubly so. That we've developed the tools and theories to understand dark energy is perhaps the most improbable thing of all. The energy of nothing, shaping everything. The invisible force tearing the universe apart so gently we didn't notice for 13.8 billion years. The quiet power that will outlast all the stars, all the galaxies, everything we can see or touch or measure. And in that strange truth that emptiness itself has energy, that nothingness can shape the cosmos, we find profound wonder. Dark energy is the universe showing us that reality is stranger than we ever imagined, that the most important force might also be the most subtle, that absence can have presence, that nothing can do something, that the void itself has power. And we are here briefly to witness it. So, here we are. 100 facts about dark energy, the force tearing the universe apart. From the shocking discovery in 1998 to the missions operating right now, from the vacuum catastrophe to the far future of everything. We've traced the evidence, explored the mysteries, and confronted the implications of living in an accelerating universe. Dark energy is the ultimate cosmic mystery, stranger than dark matter, more fundamental than any force we've studied. It dominates everything, 68% of the universe, yet we can't see it, can't touch it, can't explain where it comes from, or why it has the value it does. We've measured its effects with extraordinary precision, but we still don't understand what it actually is. Think about how recent this discovery is. The acceleration of the universe was revealed in 1998. That's within living memory. Many people listening to this were alive when we thought the universe was slowing down, when every textbook said gravity was winning, when dark energy was unknown. The paradigm shift happened during our lifetimes. And we're living through the golden age of dark energy research right now. The Vera Rubin Observatory, Euclid, the Nancy Grace Roman Space Telescope. DESI, multiple missions operating simultaneously, all focused on understanding this invisible force. The data is coming in, the observations are being made. Within the next decade, we'll have answers to questions we couldn't even ask a generation ago. We might finally understand whether dark energy is constant or changing. We might resolve the Hubble tension and figure out why two different measurements of the same expansion rate disagree. We might discover new physics, or confirm that the cosmological constant is correct, or find something completely unexpected. The suspense is real and happening in real time. Or the mystery might deepen. That's equally possible. Every time we've looked at the universe more carefully, we've found it stranger than we expected. Maybe dark energy will turn out to be more complicated than we thought. Maybe we'll discover that our models are even more wrong than we realized. Discovery works both ways. Sometimes you find answers. Sometimes you find deeper questions. But either outcome advances understanding. Even discovering how wrong you were is progress. It tells you where to look next, what assumptions to question, what new theories to develop. Science doesn't always give us the answers we want, but it always gives us better questions. Dark energy is the quiet power shaping the cosmos. It stretches space itself, silently and invisibly, pushing galaxies apart without force or violence. It's the energy of nothing, yet it determines the fate of everything. The universe held together by dark matter's gravity, but pulled apart by dark energy's anti-gravity. Two invisible forces in opposition, and we exist in the brief moment when both are significant. We live during the transition era. For 9 billion years, matter dominated. For the next trillion years, dark energy will dominate. And we happen to exist right at the crossover, when both matter and dark energy shape the universe in observable ways. Whether that's profound coincidence or anthropic necessity remains one of cosmology's deepest puzzles. The universe is fine-tuned in ways we can measure but don't fully understand. Dark energy's strength sits in a narrow range, strong enough for eternal expansion, weak enough that galaxies formed before acceleration dominated. Too strong, and nothing would clump. Too weak, and everything might have collapsed. The actual value allows complexity, allows structure, allows us. And what a strange privilege it is to be here now, to live in the era when the universe is observable and comprehensible. Future civilizations, trillions of years from now, will see only their local cluster in an empty sky. They won't have the evidence we have. They might never discover cosmic expansion or dark energy. We exist in the brief window when the cosmos reveals its secrets. Look up tonight, if you can. The stars you see are accelerating away. Every galaxy beyond our local group is receding, and that recession is speeding up. Space is stretching between us and them, gently but inexorably. Most of the universe is already beyond our reach, and more slips away every moment. The cosmic horizon grows closer as acceleration continues. Everything is drifting apart right now, not because anything is moving, but because space itself is growing. And we understand this differently than we did before. We know why it's happening, even if we don't know what's causing it. We've measured the acceleration, traced its history, projected its future. We've built the case from multiple directions: supernovae, cosmic microwave background, galaxy surveys, baryon acoustic oscillations. The evidence converges. Dark energy is real. The universe is accelerating, and that acceleration will continue for as long as physics can project, billions upon billions of years into a future that grows emptier and colder with each passing eon. The big freeze isn't violent, just an eternal fading into quiet darkness. This is the temporary nature of cosmic visibility. We live in the golden age, when matter is abundant and galaxies are close enough to study, when stars are being born and will shine for trillions of years yet, when the universe is rich with structure and possibility. But it's temporary. The universe is spreading out, and eventually it will become sparse almost beyond imagining. There's something both wonderful and melancholy about this knowledge. We exist during the brief flourish of complexity between the Big Bang and the eternal expansion. Matter condensed from the early universe, formed into galaxies and stars and planets, assembled into patterns complex enough to become conscious. And now, having become conscious, we observe that everything is slowly pulling apart. But perhaps that makes the moment more precious. We're here now, able to observe and understand. The universe is knowable, at least partially. The cosmos that created us can be comprehended, even in its strangeness. And we've developed the tools, telescopes and mathematics and the scientific method to transform mystery into understanding. Dark energy reminds us that reality is deeper and stranger than everyday experience suggests. The most important force is invisible. The largest component of existence is something we don't understand. Empty space itself has properties that determine cosmic fate. These aren't intuitive truths. They're discoveries that required centuries of physics and decades of careful observation. And we're still learning, still observing, still refining our understanding. The hunt continues, the missions operate, the data accumulates. Within our lifetimes, we'll know more about dark energy than we do now. We might understand its nature. We might confirm our models or overturn them completely. Either way, we'll be less ignorant. The universe is 68% dark energy, invisible, mysterious, but real. It pushes everything apart, determines the fate of all existence, shapes the cosmos on the largest scales, and it does this quietly, without drama, just patient, relentless stretching of space itself. We are visible minority in a universe preferring emptiness, conscious matter observing its own dispersal, brief patterns of complexity in a cosmos heading toward sparseness, and yet we're here, able to measure and understand and wonder at the strangeness of it all. The quiet breath of cosmic expansion continues. Space stretches, galaxies recede, dark energy dominates, silent, invisible, unstoppable, the energy of nothing shaping everything. And in that strange truth that emptiness has power, that the void can determine destiny, that acceleration will outlast all the stars, we find profound wonder. This is the Sleepy Astronomer wishing you sweet dreams under accelerating stars. Rest well knowing that dark energy keeps everything drifting onward, including you. The universe is stranger than you imagined, more wonderful than it appears, and more mysterious than it will probably ever reveal. And that's exactly as it should be. Good night.